Welcome to our presentation on efficient shape mapping through dense touch and vision, an ICRA 2022 submission. We consider the case of incrementally mapping objects from touch and vision for robot manipulation. This fuses robot kinematics with a partial noisy depth map and dense tactile images from a gel site sensor. To estimate local shape from touch, we develop a model that takes in gel site images and learns the corresponding height maps and contact masks. Tactile simulation allows us to scale supervised learning to a wide range of objects and ground truth. For shape mapping, we illustrate this with 2D surface measurements on the Stanford Bunny. Measurements, either from touch or vision, are efficiently fused into our spatial factor graph as local Gaussian process potentials. We generate gel site object interactions using TACSIM, an optical tactile simulator. Here's an example of simulated images on the tomato soup can YCB object. Alongside, you can see estimated height maps and contact masks from our learned model. Here are the simulation results for two such objects with a partial depth map from camera and 60 touches added sequentially. From left to right, we see the gel site images, the visual tactile measurements, the implicit surface, and the SDF uncertainty. We collect a real-world dataset of 6 YCB objects with a robot manipulator, the gel site, and the Azure Kinet. The robot circumnavigates and approaches the object at a discretized set of angles and heights, and we log the tactile images and end effector positions on contact. The object is kept stationary on a bench vise. The Azure Kinet captures an initial depth map of the object, which is partially occluded. We collect a total of 40 tactile images per object and a depth map from the Azure Kinet. We showcase results for two objects here from the dataset collected in the real world. We see similar mapping performance to that of the tactile simulation. The bottom of the objects aren't observed. We approximate them by extrapolating gel site measurements near the base. Thank you. For further evaluation results and description of our method, please refer to our publication.